What we're going to talk about today is the variation within redwood stands that we find on the North Coast. So I'm going to show you some stands, different kinds of stands, and the variation that we see when we cruise timber. And then we're also going to see how that variation changes as my sample size increases. In other words, we might look at a stand where we've only taken 5 plots, and we might look at a stand where we've taken 50, and we'll see the change in that variation, our estimate of variation, as our sample size increases. The other thing we're going to look at, which is near and dear to my heart recently, is the design of the timber cruise. Okay? We use variable plots at Green Diamond, and when you use variable plots, you have a lot of choices about subsampling your volume trees. Okay? There's a couple of different methods. One's called the volume plot count plot method. So on some plots, you measure all your trees for heights and get your volumes. Some plots, you just measure basal area. Okay? The other way you can subsample your volume trees is the method is called the big BAF, the big basal area factor method. So you might have one basal area factor for cruising your basal area, and then you might have a bigger basal area factor for cruising your volume trees. Okay, so that's the kind of stuff we're going to look at. I'm not sure I've ever seen it in the literature before. It's stuff that really excites me. So, and you might see that as I talk. And plus, I see a couple of my students here from a mensuration course I taught at Humboldt State last spring, and I don't know why you folks are gluttons for punishment. All right. So forest inventory basics. Forest inventory basics. We got to start out with a common language here. We are not going to talk about fixed plots today, although I would like to do this study in the future. What we're going to talk about are variable plots. Okay. Now, variable plot cruising, they utilize a device that has an angle, and that angle helps you select trees to measure. Now, if you have a small angle, oh, God, I'll get it eventually. If you have a small angle, you'll pick up a bunch of trees in your timber cruise. And if you have a bigger angle, you'll pick up fewer trees. And as I mentioned, in using the big BAF factor, we'll use a small angle to pick up our basal area trees, and then if we use a bigger angle, maybe we'll just pick up that one big tree right there. So that's an important concept to think about as we move through the presentation. All right, some more forest inventory basics. In variable plot cruising, that's the essential equation we use to calculate volume per acre. We take our average basal area per acre and we multiply that by what we call a V-bar, a volume to basal area ratio. Now, the average basal area per acre, that's something that we get from our smaller basal area factor, the one that we're cruising to get our basal area trees. Every tree in the cruise is used. Now, the V-bar, that's the quantity that we get from using that larger basal area factor if we choose to use it. We could also use the same basal area factor that we use to get basal area. Well, let's just take a look at that on this slide here. Here's a timber cruise where we had 93 sample points. We had 412 trees on those sample points. We used the basal area factor of 62.5. The average tree count per plot was 4.4, so to get the basal area, the 277, we just take our basal area factor and we multiply that by the 4.4 and we get 277. Okay? That's that number right up there. The next quantity, the average V-bar. Now in this case, we used the same basal area factor to determine our volume trees, that same 62.5. So you see we get 412 V-bar trees. Well, there's the 87, that's the average V-bar, if you take that average basal area per acre, you multiply it by the average V-bar, then you will get that 24,147 thousand board feet to the acre. Okay. Now also notice I have a couple of statistics here at the bottom, and this is where we're going to talk about the variation that we see in our forest types. I've printed the standard error here as a percent of the mean, and the quantity I'm going to talk about quite a bit is what I call the allowable error, and it's expressed as a percent of the mean. Let's talk about that just a little bit more. So allowable errors are computed by, first of all, we got to calculate our standard error. That's pretty straightforward stuff. You can get that at any statistics book. The key thing here, it's the standard deviation divided by the sample size. Well, since the sample size is in the denominator, as our sample size goes up, our standard error goes down. That's pretty much a universal finding. The next thing here I'm showing is the mean plus or minus a t-value times the standard error. Well, that's the formula for a confidence interval, right? The mean plus or minus a t times the standard error. And the reason I'm showing you that is that that's where it comes into the allowable error. See, I got that 1/2 width of the confidence interval divided by the mean. So that allowable error is just a percentage of the mean. So if I go out there and I do a timber cruise and I come back and I tell you my answer is plus or minus 10% of the mean, it has an allowable error of 10%. Okay, I love confidence intervals. That's why I've chosen to present my results in terms of this allowable error, and it's relative to the mean. Okay, so as we go through this presentation, keep in mind, once again, that the allowable error is just like a confidence interval divided by the mean. Okay, so featured in this presentation, we're going to take a look at the allowable error for different stand types. We're going to see how that allowable error decreases as my sample size increases. And then we're going to examine how that allowable error changes depending on how I design my sample, right? If I subsample my trees these two different ways, I might choose to use count plots and volume plots, so we'll see the effect that that has on the allowable error. And then if I subsample my trees using a big BAF method, we'll see how that changes my allowable error. So this is an allowable error curve for a Douglas fir redwood stand up in Smith River. And the way I construct this is I take my first plot, or my first two plots, I calculate the mean, and then I calculate the standard error, make that confidence interval, and then divide by the mean. And since I only have two plots in that first calculation, it has a huge variance, right? When I only have a sample size of 2, that's typically what you find. So then I add the next plot, 3, and compute the mean, compute the standard error, calculate the confidence interval, do the division, get my allowable error, and then you can see my curve starts coming down. Well, by the time I have 10 samples for calculating my statistics, right, my allowable error is starting to drop down quite a bit. And then by the time I add 40 samples into the mix, my allowable error is starting to stabilize. Okay, keep in mind it's 1/2 width of the confidence interval divided by the mean. So what can we deduce from that chart? The allowable error starts out big and it decreases as sample size increases. And once again, that's to be expected because as sample size increases, that's in the denominator, it makes the standard error go down. Okay, and then the other feature I want to bring to your attention, the value of increasing sample size diminishes as sample size increases, right? When I keep adding plots to the mix way out here, when I'm up to 90 and 100 plots, the value of that extra plot is not very much, right? It's not adding to what I really know about that stand. I'm wasting my time. It's a good thing for a forest manager to know. So what I've showed you here are the allowable error curves for a variety of coastal North Coast stand types. These stands down here, these are Douglas fir redwood mixes, this gold line and that black line. These next two right here, the blue and the purple, that's a redwood stands. And then these two up here are tan oak Doug fir stands. So you can see that the variation is dramatically different depending on what kind of forest type or stand type I'm looking at. We see this over and over again at Green Diamond. So now let's suppose I choose to put 20 plots in each of these stands. Well, when I come back for these tan oak Doug fir tan oak Doug fir, I'm going to tell my boss, yeah, I know the mean plus or minus 55%, right? And then I tell him, well, for this nice Doug fir redwood stand, I know the mean plus or minus 20%, and it only took me 20 plots. And the average of all that, if you play with the numbers enough, is about 40%. So if I only put 20 plots out there in all my stands, the best I can do is tell my boss, well, your volume is X plus or minus 40%. Might not make him feel too good. So let's suppose I put in 60 plots in each of those forest types. In this case, you can see I'm down to about 12% for the Doug fir redwood stand, and my hardwood Doug fir stands have come down to about 40%, and my mean is about 25%. So by putting in 40 extra plots per stand, I'm now down to about an average of 25%. Okay, so I wanted to study this because typically when we cruise timber, we select a sampling design, and that's what we do. We might pick a basal area factor to cruise our plots, and then we'll pick a big BAF. Maybe it's 3 times the basal area BAF, or maybe it's 4 times, but that's what we do. The other thing we might do is we'll say, oh, let's have 2 count plots and then do 2 volume plots. That way we don't have to measure heights and form factors and all that stuff on every tree, on every plot, right? We can save a little money. But what I wanted to do is I wanted to understand that. If I make that decision, what does that mean to my allowable error? So we laid in this study. This is a stand that we have. It's about 10 miles up Fickle Hill Road. It's L-shaped, and we put in 93 plots, and 93 is overkill. It just is, but if you really want to understand what's going on with your statistics, you have to go to the far end of your range. You really want to pin down that right-hand side of that allowable error curve. We met out there first day, talked about the cruise, the measurement standards, this very complicated design where we were going to use different basal area factors that really had to be well understood. If it's not, at the end of the day, you're going to get garbage that you can't analyze. Now this stand, we chose this stand because it's really variable. It's got a lot of different species out there. It's got tan oak, redwood, Douglas fir, grand fir, red alder. It was partially harvested in the past, so it really has a lot of variation with respect to size classes. Yeah. One of our new employees, a recent graduate from HSU, Chelsea, took these pictures. Well, this is what the data looks like. Right? There's plot 1 right there. It came in at about 3,000 board feet to the acre. Okay? There's plot 2, way up there, somewhere around 35,000 to the acre. Right? Look up here, we got one plot came in at 50,000 to the acre. And then I got some down here. No trees on the plot. Lots of variation. Lots of variation. This is really common. really common in the natural stands, the second growth natural stands that we manage on the North Coast. So what I've done for you here is I've laid in the mean, that's the red line, as I add samples to my mix for calculating the mean, right? The mean, when I only have one sample in there, is just that 3,000, right? But as soon as I add the 35,000, my mean jumps up to 20,000. As soon as I add the next plot, it goes up a little bit more. Well, then I add that plot, it drops down. But you need to, I just want you to grasp the concept of how this chart's constructed. I'm adding plots, and each time I add a plot, I recalculate my mean. Okay? Then I can also recalculate my standard error, and then I can calculate my confidence interval, and that's what this is showing. Early on, when I only have two plots, lots of variation, right? So there's a huge confidence interval about my mean. In this case, look, it's 20,000 plus or minus 30,000. Two plots, right? When I get way out over here at 93 plots, right, that's my 24,147 board feet to the acre. And my allowable error, remember it was like 12%? Well, that's 12% right there, 12% of the mean. So that's what I look at when I want to analyze my data. So all I do now is I'm going to convert this to my allowable error chart, okay? All I did was I took, once again, the half width of that confidence interval divided by the mean, and I get this. Now, this curve represents the situation where every volume tree was measured. 412 trees in all 93 plots were used to get this curve. So this is the best I can do. Every tree in the cruise was measured for height and diameter. Very expensive. Okay? So what happens if I analyze these data a little differently and I look at them from a count plot, volume plot perspective, right? So that's what this chart's going to show us. The blue line, oh man. The blue line is for the situation where the basal area factor used to cruise basal area was the same as the basal area factor used to get volume. Okay. Okay. I can get this wrapped up real quick. Okay, so the next red line, that's where I use a basal, oh, excuse me, this is count plots, volume plots. Excuse me, got to back up. This blue line is using all plots as volume plots. The red line is using one plot as a count plot and three plots as a volume plot. Well, as soon as I go to two count plots, two volume plots, I get this line. And as soon as I go to three count plots and one volume plot, I get this line. But this is what I want to draw your attention to. Look way out over here. In order to get plus or minus 20% using two count plots and two volume plots, I have to install 70 plots. Whereas if I measured every tree, I only have to get 30 plots out there or so to get the same allowable error. That's the message I really wanted to communicate to you folks, is how you design your sample is really going to determine how many plots you need to take. Okay, that's a key point. If we can look at the next one, this is where the basal area factor is increased, and quite often folks will use a basal area factor that's triple. The big BAF is triple your regular BAF, and that's this line right here. And in this case, look at this. You get plus or minus 20%. You need, I don't know, 80, 85 plots. But once again, to get the 20% using every tree as a volume tree, you only need 30 plots. Okay. One last thing here. When we use the big BAF, this is a real important point. When I use every tree, my volume estimate per acre was 24,147. As I went to bigger BAFs, that volume per acre went up. So this is like bias, right? If I use the big BAF of 4 times my regular one, I'm going to tell my boss there's 25,570 board feet per acre out there on average, when it's really this. All right, this is what I recommend. If you have a really variable stand, I would recommend measuring all your trees for volume. I would not subsample using the big BAF method, and I would not use count plot volume plots, okay? If you're a timber cruiser and you're an owner of timberland, you make your consultant show him the allowable errors or the standard errors. You want to know the confidence interval that's associated with the inventory figures he gives you. There's a lot of science behind determining sample sizes. Well, do that. Like I showed you, you know, once you get beyond 40 or 50 data points, you don't need much more. So you really got to be careful about how big you want to make your sample size because you're going to pay money for that. And this is a good one. I would highly recommend replicating this analysis on your different stands that you might have in your forest. Certainly we're going to do this at Green Diamond. Okay? Thanks for a little extra time.
So, one comment, I didn't see you out in the field with the group. I didn't notice that. But the question was, how could you integrate your method with the methods we just heard about in terms of stratifying based on some of the remote sensing you can do in advance and really think more strategically instead of a systematic grid?
Well, you know, I think that's some excellent concepts there. I really like the idea about, you know, moving your plots apart because what I just said, we need fewer plots. I don't want to put them out there on any systematic grid. And I think Pascal has some good ideas about where might I want to put my plots to really extract the maximum amount of information when I'm out there. Okay. So some good ideas there.